So hello everyone, me and Charlene here will be presenting the paper titled Reinforcement Learning Based Speech Enhancement for Robust Speech Recognition. Now, two key concepts discussed in this paper are speech enhancement and automatic speech recognition. So I would like to discuss these first. ASR systems face issues in noisy environments, obviously. So speech enhancement is a way to generate clean and undistorted speech signals before feeding it into the ASR system. Now, there have been many traditional speech enhancement approaches, which include various signal processing techniques like auditory masking, DFT, etc. We won't delve into those that goes into heavy signal processing territory. However, some deep learning approaches have delivered great results in the recent years, and this is one of the papers which builds upon them to suggest a reinforcement learning based setup to improve speech enhancement for automatic speech recognition systems. We'll quickly discuss an overview of the key aspects of the paper before diving into the details. Now, the proposed system identifies something called an ideal binary mask to be used for speech enhancement. We'll discuss ideal binary masks later in this presentation. Also, usually ASR systems are very complicated and have language processing modules, speech processing modules, and hence they are not directly modified. Also, ASR systems also are often provided by a third party. And hence the ASR module in this entire setup and even in the experiments is considered to be fixed for the purposes of this paper. The paper tries to build a speech enhancement method to supplement the fixed ASR system in noisy environments. Now, this paper uses some interesting evaluation metrics. Supervised speech separation methods train machines to cast noisy speech to the target clean speech. Now, most of them use mean square error as a loss function. However, mean square error is not always the best choice because it does not match the human auditory perception as well. This paper uses a short-term objective intelligibility score and perceptual evaluation of speech quality. Now, these scores mean exactly what they literally seem to mean, and they are closely related to the human auditory perception, and they are widely used in speech separation research and speech processing related research as evaluation criteria. Another metric that this paper uses is the character error rate, which is pretty straightforward. It is the percentage of characters from the speech that the system did not identify correctly. So a character error rate of say 10% means that every 10th character from the speech was not correctly identified. Coming to the results, the proposed method is tested at two SNR conditions. SNR represents the signal to noise ratio. It is a signal processing term, which is not exactly the ratio of signal and noise, but effectively measures the relationship in a similar way. This is again a signal processing concept, so we are not going deep into that. Now, the proposed system has effectively reduced the CER by 12.4% at 5 dB SNR conditions and 19.23% at 0 dB SNR conditions. Now, here 0 dB also does not mean absence of sound and noise. The SNR is actually a logarithmic equation. So 0 does not signify nothingness. 0 does signify some sound. This paper is also somewhat mathematically heavy. So we'll start looking at some notations and some equations from here on. We'll also cover some important techniques that this proposed system builds upon in the next couple of slides. Coming to the short-term Fourier transform, in very rough terms, performing a Fourier transform on the sound signal would give us data points that we can process. We can convert the input signal from time domain to frequency domain via the short-term Fourier transform. And now in this case, Y represents the input signal, and the input signal can be represented as a sum of the clean signal, which is S here, and the noise, which is N here. And we take something called the Mel frequency spectrogram of the signal, and we divide it into C chunks. Now, this notation for signals in chunks would be used throughout the paper. Also, the Mel frequency spectrogram is again another concept that we won't be diving into. Just know that there is the variable p here represents something called frames, and it can take only two values, 1 and 2, and the experiment would be using both these values to see what performs better. Now, as mentioned earlier, one very important speech enhancement technique that this paper uses is the ideal binary mask. So with ideal binary mask, for each time frequency unit, if the SNR, if the noise is above a threshold, that unit is masked. And if the noise is within acceptable limits, that unit is kept as is. In simple terms, I'm sorry, I forgot to mute my call. In simple terms, uh, it is just a vector with binary values, which when multiplied with the signal vector, the zeros of the binary values mask the noises in the speech vector, and the ones keep the good speech from the speech vector. So S hat here is the enhanced speech, which is obtained by using the binary mask B on the input speech Y. Note that all of these are vectors here. B, the Y, the output speech, all of these are vectors here. An ideal binary mask is generated from the training data via the equation, via this equation here that I'm pointing to. So if you look here, the equation uses the step function on the entire equation, which means that the output that we get for the binary mask would contain only binary values. Now, the proposed technique in this paper relies on generating and selecting the appropriate binary masks to enhance the speech. So this is basically a very important thing that will be used through the paper. Another method which has been used for speech enhancement and this paper builds upon is DNN-based speech enhancement. Now the DNN-based model is relatively straightforward. A DNN-based speech enhancement model simply uses noisy and clean pairs of inputs as training data. And again, the input noisy data is divided into some chunks for input. And the DNN uses the sigmoid activation function between layers, and finally a linear transformation at the end to get the enhanced speech, because the sigmoid function actually gives only a range of values. So you use a linear transformation at the end. And the model simply uses the mean square error between the enhanced speech and the actual clean speech as the cost function. So these are the techniques which are related to the proposed method and what the paper would build upon. At last, we would discuss reinforcement learning very briefly. I'm sure you all are. Oh, okay. I see some things in the chats. Okay, there are some confusions related to the short-term Fourier transform. For now, Shivendra, for now, just understand it will just give you data points to utilize, right? The speech signal is a continuous signal. So you need to be able to process it within machine learning models, within deep learning models, and you need data points for that. So it gives you chunks for that. You can read up about it later because it's a very heavy mathematical concept. So again, going on to reinforcement learning. Reinforcement learning is a mechanism where wrong actions are penalized and correct actions are rewarded, in a way similar to how humans learn by making mistakes and continuing to move towards the goal until we finally arrive at a maximum reward position where it cannot be modified anymore. Now, using rewards to penalize the model is different from using the mean square error. The mean square error simply represents the difference between the output and the generated ideal input. But with reinforcement learning, you can define equations for rewards which may not necessarily correspond to the exact differences between training output and actual output, and you can use the metrics that correspond better to the human auditory response, which will improve the ASR system better than the MSE score. So with RL, actions taken by the system are adjusted based on previous rewards, and the system keeps trying to reach at the best possible reward. So this paper uses reinforcement learning and rewards to improve the system performance for the ASR system. Now, Charlene will take over and present the speech enhancement system proposed in this paper. Charlene, you can share your screen now, please.
Do you see my screen?
I'll just stop sharing mine so you can share
Okay.
yours.
Yeah, I just shared mine. Let me know if you don't see it.
I can't see your screen.
You can see your screen.
Okay, great, thanks.
Okay, all right, I can see your screen, thanks.
Okay, great. Yes, so the proposed system in the paper, there are 3 modules. IBM clustering module groups IBMs, as Prana mentioned before, ideal binary mask from training data into clusters. Action estimation module generates an estimated action through DNN. And lastly, target action determination module selects IBM and feeds into ASR, which generates an action update. So this is a graph from the paper. It is clearly illustrated. So I'm gonna go to the next, the first module, IBM clustering. In the IBM-based speech enhancement system, an ideal binary mask filter is computed for each feature vector. And as you can see here, our input binary mask, it is collected from training data using the equation from step function, this function mentioned by Parna. So in this case, IBM clustering module groups the entire set of IBM vector B hat into 32 clusters based on k-means algorithm. The ensemble of those clusters is denoted as G hat. We're going to use this G hat later on in other modules. So values in the ideal binary mask vectors are binary. So Hamming distance is used to compute the distance between 2 vectors in the k-mean clustering. The action estimation module is to estimate the initial action vector. To effectively use the training data, we first pre-train the DNN model by placing YC at the input. YC is our input speech, and IBM vector B hat at the output instead of the clean speech. Basically, we're trying to output an ideal binary mask. The mask is like, the ideal binary mask would be like what frequency is considered clean, what frequency would be considered as a noise. The DNN model was then retrained with additional hidden layer to compute a-dimensional action vector AC at C's chunk. The cluster index AC with maximum value was determined here. It is used in the next module. Here we have the argmax function. And the cost function here is MSE. And lastly, softmax operation is used in the final layer for the retrained model. Going to the next module, it's the last module. This is where we take the estimated action vector to then select IBM. And then, as you can see in the graph on the left here, the input action vector will go through IBM selection, then speech enhancement, then go to ASR. And then ASR module will provide 2 rewards, and we're going to use those 2 rewards to update our action vector. So starting again from the beginning, so IBM selection function will select GA, which is one IBM cluster to enhance the original input with respect to index A equal to AC. So after enhancing the chunk vector, which makes up the GS, both input noise and IBM enhanced speech will be fed into ASR. Before feeding those the input noise and IBM enhanced speech into ASR, we have to translate them from frequency domain back to time domain, because ASR will only take time domain signals. And then after they're fed into ASR, the ASR will produce the utterance-based error rates. ZY for original input, ZS apostrophe for enhanced speech. We're going to use those two errors to calculate our rewards in the next slide. Our reward function, so we have two reward functions. The first one, the big R, is a tangent function of basically the difference between the error of the input speech versus the error of the enhanced speech. So alpha here is a scalar factor, which is set to 10 in this study. For this equation, the positive R reward denotes a larger error rate, which means that the error of the input speech is bigger than the error of the enhanced speech, which is suggesting that the enhanced speech can provide better recognition result. On the other hand, a negative R would mean a smaller input speech error than the enhanced speech error, which means that the enhanced speech gives bad recognition performance. So I believe the first reward calculation should be straightforward. The second one would be a chunk-based time variant reward. So in addition to our utterance-based reward, big R, we also consider the chunk-based reward because the action for each chunk vector may act and contribute differently to the enhanced speech, which may give positive contribution to the ASR. So the author basically created this reward. As you can see here, EC hat in the equation 11 is the weighting factor. It's between 0 and 1. It is the normalized square error at this chunk. So when you select a bad IBM vector, I mean, I wouldn't say bad, the IBM vector doesn't fit, the normalized square error EC hat is large. So when the EC hat is large, the accordingly RC, which is our small RC, which is our chunk-based reward, will also be small. This is to penalize the wrong action. And the big R reward, alternance-based reward, and the time-based reward, small RC, will affect the action update collectively. As you can see here, so we have, okay, here we go. So this is the action update. So when big R is bigger than 0, smaller than 0, it will affect the action update. So does small RC. So I'm going to talk more about the action update function. To update the action vector AC, we first determine two different action indices, A, B hat, C, and AC. To obtain the A, B, C hat, we first follow the ideal binary mask-based SE system to determine an IBM vector, which is then used to locate the closest cluster in G hat. G hat is a group of IBM clusters. The located cluster index would be A, B hat, C. You can see, yeah, here. On the other hand, the cluster index AC, this one, is determined by the argmax function presented in the action estimation module. And the updated action will affect the cost function from the action estimation module. This is our action, this is a MSE cost function for the DNN action estimation module. This will backpropagate to retrain the neural network. So after performing the training on DNN with associated object function, the illustration on top, figure 3, this shows the testing process. from the illustration, the well-trained DNN module is applied on a noisy STFT MPS speech, which means that it is basically a frequency domain noisy speech. The estimated IBM indices are then used in combination with argmax function for each chunk to further enhance the input noisy speech and provide the enhanced speech in the output of IBM SE function. So here we will have a enhanced speech output, and this will get inputted to ASR to conduct the recognition process. So our data set would be an 198-hour-long Mandarin Chinese broadcast news corpus. Noise would be the baby cry noise. The author actually injected the noise into the clean speech. So the baby cry noise waveform was divided into two parts. The first part was artificially added to the 460 training utterance with signal to noise ratio level at 5 dB. The second part was artificially added to the 30 testing utterance. So we established two RL-based SE model with two different parameter P for the chunk vector. Both RLSE1 and RLSE2 were composed of one hidden layer with 64 nodes and 32 for the output nodes. The input dimension of RLSE1 is 704. For RLSE2 is 640. So we have a different parameter F for those two models. Parameter F provides the context information, and it is related to the to our chunk vector. So in the next slide, we have obtained some results from the author and some speech demo. I think Parna will take it from here.
Yeah, I'll just share my screen again. I guess you guys can see my screen now.
Yep.
All right. So despite the fact that the goal was to improve the automatic speech recognition performance, the RL-based speech enhancement system also denoised the input speech, and studies have reported a positive correlation between intelligibility scores, which means noise-free speech, and ASR performance. So in the experiment, RLSE2 performed better than RLSE1. And in the figure here, you can see noisy and clean spectrograms as figures A and B. And when you compare these with the results of enhanced speech here in the second row, you can see that the output spectrograms look a lot more like the clean speech spectrograms. We got in touch with the authors, and they were kind enough to send us one of the set of audios from the test data. And so the first audio I will play here is the input speech, which has the noise and the input speech. Let's see if you guys can hear it. Were you guys able to hear it?
I couldn't hear it.
Okay, all right. I'll just check my settings once. I'll play these audios for you guys a little later. I think I just remembered there are some different settings that I have to work on with these. Okay, so moving on to the results that which are numbers, and we can see right now. So the authors designed another set of experiments where they use the same 32 IBM vectors, but the one nearest neighbor approach used to find the IBM vector did not perform as well as compared to the clustering method. both RLSE1 and RLSE2 provided better recognition results than the noisy speech. If you look at table 1. Also, you can also see that the STOI scores were better for both the models. For both the models here, the STOI scores were better. With PESQ scores, the RLSE1 does not perform as well. But also, one thing to be noted is that the correlation between ASR performance and PESQ scores is not as high as the correlation between STOI scores and automatic speech recognition. In conclusion, this study serves as a proof of concept for future work in using RL to create speech enhancement systems for fixed or black box like ASR systems. And with the given experiment setup, the proposed system reduces the character error rate by up to 19.3% depending on the SNR conditions. Future improvements could include more training data with different noise types, different languages and different SNR levels. And that is where the IBM clustering will also help with grouping the IBM masks for similar noises together. So we would like to thank the co-authors of the paper, Chao Yuan Wang and Yi Liang, for providing us with the recordings and from the set of test data and for answering our questions. That will be all from our side. We know this paper was somewhat mathematically heavy, but we hope that you found it interesting. We can answer any questions that anyone has now, while I try to figure out how to have you guys listen to the audio. Anybody has any questions?
Yeah, is there GitHub or something that I can look at for the code?
No, actually, we contacted the authors. The authors said that the ASR system that they used, that is confidential, and some more components of the system that they have used are confidential. So he did not give us the code, and it's not up anywhere. But he did give us the audios, which I am trying to work out.
Oh, okay. All right.
Yeah.
So it's all confidential. Okay.
Yeah, like enough parts of it are confidential that we could not mimic the system either, and we could not get the code from the author.
All right. Okay.
Okay, I guess this should do when it comes to the audios. You guys can still hear me?
Yep.
Yes, we can
Okay.
hear you.
Yeah, I'll just play the audio here. So this was the clean audio. This was the input which was noisy, and this is the clean output. Were you guys able to hear the noisy input?
Yep.
Yeah, all right. So I'll just play the clean output right now. It is completely clean. It's test data. So I'll just play the output from the speech enhancement now. So you can hear that there is some noise still there. You can feel that it's not completely clean, but it still has not distorted any speech and has removed enough noise to improve the automatic speech recognition here. That's all. That's all from us. Any other questions here?
Hey, Prerna, just a basic question, like the existing speech recognition, like NLP systems and this one which you have presented today. So what is the major difference you found, like performance wise or like the accuracy part? What is the major difference between the two models?
Okay, first of all, those NLP based speech recognition systems, that's the ASR black box system I was talking about when I was saying that it has too many things. It has language processing models, it has speech processing models. So here we are assuming that that entire NLP based thing, it's a black box here. What we are doing is we are just enhancing the speech to be input into that thing. We are not at all touching the speech recognition models. We are just improving the speech quality for the understanding of the ASR model. Does that answer your question?
Okay, so only thing I was asking, like, do we know, like, is it performance wise or like accuracy wise the better model, like, or instead of an NLP, or you think like they both have their own advantages? That was like my primary.
Um, so you mean NLP for speech enhancement?
Yeah,
I'm sorry,
can we
I didn't
use
get
that? Yeah, can we use that for like speech recognition? I am aware, but are there any NLP speech enhancement that are similar to this RL
it.
based speech enhancement? Hmm.
NLP is natural language processing. It's
Yeah.
language processing. What the authors have presented here is it's not related to language at all. It's just related to speech. You can use this for different languages. So
Okay.
natural language processing and speech enhancement are different concepts.
Yeah, here we're mostly denoising and trying to use ideal binary maps to create a cleaner speech to be input to ASR to the NLP system, so it perform better.
Okay. Thank you. Got it.